Okay guys, let's understand a bit about E-cell calculation. Suppose there is a reaction A plus B giving you C and D, where small a, b, c, d are stoichiometries of the reactants. Alright, and now what's the Nernst equation for electrode potential? This is the Nernst equation for electrode potential. E cell is equal to E0 cell, and these are the factors. Now N is number of moles of electron, and this is concentration of C raised to its stoichiometry, concentration of D raised to its stoichiometry, concentration of A raised to its stoichiometry, and concentration of B raised to its stoichiometry. It's obviously it's equilibrium constant, which we have studied earlier. All right. Okay. So we can also write it as log k to the base 10. Fine. Okay. Now let's take up an example. Zinc reacts with copper. What I have chosen is the same as we have tried in Daniel's cell. Zinc electrode, copper sulfate, zinc sulfate, and copper. All right. Now zinc, in case of zinc, it lost 2 electrons and got oxidized to Zn2 plus, whereas in case of copper we had found that it gained 2 electrons and got reduced to copper solid. Started with zinc solid, ended up with copper solid. Just to recap, we had seen that the anode, which was zinc electrode, kept on reducing in size, whereas cathode, which was copper electrode, kept on increasing in size owing to deposition of solid copper. So this was the reaction that we had tried. Now E cell, as I told you, Nernst equation, jotted it down. Now instead of C, D, A, B, I've jotted down the relevant ions and atoms. All right, copper solid. So now what happens is, let's understand this first. Now N is number of electrons transferred or involved in redox reaction. Here obviously 2 electrons are involved, so N gets the value of 2. N gets the value of 2. All right. Then concentration of solids and pure liquids are taken as unities. Solids. So here what we got is copper solid. Here also we had zinc solid. So copper solid and zinc solid. So this was also one unity, and this also was one unity. All right. Now this one comes, why? This comes because concentration of zinc ion and copper ion is 1 molar. And why is it 1 molar? Because what we are doing right now is we are talking in terms of standard state. All right. So we have taken 1 mole, and we want to see what happens to Nernst's equation if we choose standard state condition. All right. All right. So what we did is we fitted in all those values. So this resulted into 1. So, and we know log 1 is 0. This entire factor disappears. All right. Now what happened to zinc ion and copper ion? Now since it had concentration 1, so it got value 1, and copper got value 1. All right. So that's it. So ultimately what happens is it comes to 1. Now 1, we know log 1 is 0. So this entire factor disappears. All right, entire value disappears. So what we end up is with E0 cell. So just wanted to give an example, give an evidence rather, that how if we take concentration as 1, then this factor disappears. All right, this factor disappears if we take concentration 1. All right, now, so what are the standard state that we had seen earlier? 25 degrees Celsius and 1 atmosphere pressure and 1 molar concentration. So that has to be there, right? So it comes to 1. So this disappears. So E cell now becomes E0 cell, that is E standard cell. All right. Now let us get into a numerical where we are changing values of concentration. All right. So again, the same for Nernst equation. Another thing that I wanted to inform you is this was standard state electrochemical condition. Then what was this? What was this? This was correction for non-standard state condition. Non-standard state condition in the sense maybe the reaction might have been done in different temperature. Maybe the reaction might have not done at same pressure, or the concentration have been different. All right, so that's why we call it as non-standard state condition. Why should all the time reaction be done in standard condition only? Okay, so here what we have done is, what we have varied is the concentration. So you can check out over here, zinc, silver. Obviously, when zinc is being oxidized, so zinc is anode. And if it is anode, in ECS table, this has to be in lower part of table, that lower part of the table, and this has to be above zinc, because here this is acting as a cathode. So this zinc is being oxidized and silver is being reduced. All right, now another interesting that you have got to make a point of is, now here there are two silver ion. All right, two silver ion. Why? Because see, when silver is getting reduced, it's getting reduced only by one electron because the valence is 1. Whereas zinc is giving out 2 electrons. So in order to adjust that 2 electrons, we have got to balance electrons. So I have got to take 2 silver plus. All right, so that it will consume both the electrons provided by zinc on oxidation. All right, so balancing of electrons are very much essential in this step. All right, so we did that. All right, now let's just apply Nernst equation, substitute those values. So I have substituted here. So I have substituted a product of concentration of products. So here it is zinc. All right, so concentration was 0.02. So I jotted down here this concentration. We have to take a solid, so we have to consider it as unity. So 1 but 2, so square. I hope you remember that CD stoichiometry. All right, and then again here now we come to reactant zinc 1 unity and silver 0.01 stoichiometry square. All right, so when we do that, so we, for time being, we keep it here. We come to finding E0 of cell. Now since we have taken silver and zinc, so we have from ECS we get the value of silver. As I told you, ECS, if you remember, ECS I told you was reduction potential. All right, so this is reduction potential, and in case of silver, no problem, silver is getting reduced itself as it is cathode. So whatever is the value in ECS table is 0.08, so we can take it with positive sign as it is. In case of zinc, again what is given is reduction potential, so it is Zn2 plus giving you zinc, but what we need is reverse thing. So this we have got to multiply with negative to get oxidation potential, because in ECS we have the reduction potential. Fine, so that's what we do here. So E anode, this is what is anode, so minus of this plus as it is, since it is reduction, so final value comes to 1.56. Wow, this is very close to our cell that we use in our daily use. All right, the cell that we use for our daily use, the value is very close to it. All right, so maybe you can do it. No, but it would be very expensive using silver. Okay, anyways, getting back to this, so what we do is E cell, so we substitute those values. This is what is the constant value 2. Why 2? Because 2 electrons shifting of redox, 2 electrons involved in redox, so 2. Then this becomes, I've just shown you a bit of calculation over here, how to do this calculation. So 0.02 into 1 square upon 1 into 0.01 the whole square. So maybe the decimal you can remove here, and 1 square you can remove, so it comes to 2 upon 0.01, which comes to 200, right? So we got this 200 over here. Now something very important, the only log to be found from table, no anti-log. All right, because it is log. So what do? We just check out log for 200. We know the characteristic comes to 2, 1, 2, 1, 2, 3. So characteristic comes to 2, and if we see 20 in 0, it would be 0.3010. So our value for log 200 to the base 10 is 2.3010. All right, and when we multiply, what we get is 1.53 volts. So this is the volt that this cell would, this cell with zinc anode and silver cathode would produce, which is very close to our value of our cell that we use in our daily life. All right. All right. So that's how we calculate our E of cell. All right. So understand it well and apply it for your numericals. A few things that you have got to keep in mind is certain values you have got to by heart. Now those values are root 2 value, root 3 values, root 5 values, because this would be used, they would be giving type of sums where these values would be used, and you won't be having logbook to see these values, to check these values. All right. So and log of 2, 3, 4 also you have got to keep it in mind. All right. Okay. Having explained you this, I presume you would be trying some numericals and checking your capabilities out, and you would do well. All right. All the best.